Welcome to Module 5.5. In the previous module, we have made our acquaintance with the frequency response, and the frequency response leads to a natural classification of filters according to which frequency bands they attenuate or they boost. For instance, a low-pass filter would be a filter that only lets low frequencies go through and kills high frequencies. Vice versa, a high-pass filter lets high frequencies go through and attenuates low frequencies. Now, these concepts are actually everyday concepts. You've certainly used a stereo system where you have knobs with which you can control the tone, the treble, the bass, and the middle. Let me give you an example of how these knobs can affect the quality of a sound. So we will get this guitar that's been here for a while now and connect it to an amplifier, a virtual amplifier in GarageBand, and see how we can change the sound. So here we have a standard guitar amplifier, but simulated digitally. We start with all the knobs in the middle position to have a neutral sound, which will sound like this. If now we've set the bass and middle knobs to 0 and leave only the high frequency, we get a very tinny sound. Conversely, if we only let the low frequencies go through, we get a very dark sound. Okay, so now that we know what bandpass, high-pass, and low-pass filters do to a signal, the question is, what is the best filter in each category that we can think of? And in this module, we will introduce the family of so-called ideal filters, which are really the best filters that we can think of. Now, these filters are ideal, unfortunately, in a platonic sense. They can be thought about, but they cannot be implemented in practice. But nevertheless, they will remain the paradigm that we will try to get as close as possible in our real-world filter design problems. Hi, and welcome to Module 5.5, in which we talk about ideal filters. In this module, we will start by defining a classification for filters in the frequency domain this time. Then we will talk about ideal filters, and we will revisit the demodulation strategy that we introduced in Module 4.8. So we can classify filters according to 4 broad categories based on the shape of their magnitude response. Low-pass filters are filters that let the low frequencies live and kill everything else. High-pass filters do the opposite. They let high frequencies go through and they kill low frequencies, in particular frequencies around 0. Bandpass filters let only a band of frequencies go through in the middle of the frequency band. And all-pass filters are filters for which the magnitude is a constant over the entire frequency band. So this classification really mirrors the classification of signals that we introduced in Module 4.8. The moving average and leaky integrator, as we could see in the previous module, have a frequency response which is concentrated around the origin, so they belong to the low-pass filter category. We can also classify filters according to their phase response. This is less common, but it's important to know whether a filter has a linear phase characteristic or a nonlinear phase characteristic. So, what is the best low-pass filter that we can think of? Well, as we said, the low-pass filter lets low frequencies go through and attenuates or kills high frequencies. So, an ideal version of the low-pass filter would leave frequencies in the low band untouched and would completely attenuate, completely kill frequencies in the higher band. So the magnitude would be 1 over the pass band and identically 0 over what we call the stop band. To make matters even better, we would require the magnitude response to be a real function so that the filter has 0 phase and therefore introduces no delay. So if we call omega c the cutoff frequency, where the frequency response transitions from 1 to 0, we can say that the ideal low pass has a bandwidth of omega b, which is equal to twice omega c. Formally, we can write
the frequency response of the ideal low pass, big H of e to the j omega, is equal to 1 for omega between minus omega c and plus omega c, and 0 otherwise. And remember, whenever we write a specification like this, we tacitly imply the 2 pi periodicity of any frequency response, of any Fourier transform. So this means that the ideal low pass has a perfectly flat passband, which is identical to 1, has infinite attenuation in the stop band, and again has 0 phase and no delay. Let's try and compute the impulse response from the frequency response by taking the inverse Fourier transform of big H of e to the j omega. So we can write the inverse DTFT formula, which we know by heart. And since big H is a 0 from omega c to pi and from minus pi to minus omega c, we can change the integration limits and just integrate from minus omega c to plus omega c. Incidentally, over that interval, big H is equal to 1, so this simplifies to just the integral of e to the j omega n between minus omega c and omega c. And if we solve that integral, which is rather easy to do, we get 1 over pi n, that multiplies e to the j omega cn minus e to the minus j omega cn divided by 2j. We know from Euler's formula that this is equal to the sine of omega cn, and we are left also with pi n at the denominator. So we can plot this impulse response, and we find out that it has a nice oscillatory shape. We also notice that it is an infinite support impulse response, and as opposed to the other infinite support impulse responses we've seen so far, now the support is infinite both to the right and to the left. Now this is a problem because it means that no matter how we compute the convolution, we will always have an infinite number of operations to compute. So this low-pass filter cannot be exactly implemented in practice, and we will spend quite some time in the rest of the module to find ways to approximate this ideal behavior with computable filters. Another problem with the impulse response is that it decays very slowly in time, as 1 over n as a matter of fact, and so we need a lot of samples to get a good approximation of the impulse response if we were to implement the filter directly. In spite of the shortcomings, the ideal filter, the ideal low-pass filter, is so important that we use 2 special functions to describe its impulse response and its frequency response. So we start with the rect function that, as the name suggests, looks like a rectangle, and it is indeed the indicator function on the real line from 1/2 to -1/2. The sinc function, in this particular case it's a normalized sinc function, is simply the ratio between sine of pi of x divided by pi of x for all real numbers other than 0, and it is prolonged by continuity in 0 to the value of 1. Note that the sinc function is equal to 0 whenever its argument is a non-zero integer, because in that case the sine of pi x becomes 0. With this notation in place, we can express the ideal low-pass filter in canonical form. The frequency response, h of e to the j omega, will be simply the rect of omega divided by 2 omega c, where omega c is the cutoff frequency of the filter. So it will look like that. The impulse response will be the sinc function normalized by omega c over pi, both in terms of its argument and in terms of magnitude. So here's an example with omega c equal to pi over 3. We have a low-pass characteristic with cutoff frequency pi over 3. And in the time domain, we have sinc of n over 3 multiplied by 1/3, which means that every third sample, as we said, is going to be 0, because every time n is a multiple of 3, the argument of the sinc will be an integer. So here's a little known fact about the sinc function. The sinc function is not absolutely summable. The proof is not too complicated, it only involves basic calculus, and you can find it in the references. As a consequence, the ideal low-pass is not bibostable. We can use the technique that we developed in the proof of the stability theorem. And so, for instance, if we take omega c equal to pi over 3, the impulse response of the ideal filter will be 1/3 sinc of n over 3. We build an artificial bounded input signal, which is simply the sine of sinc of minus n over 3. And so if we compute the convolution in n equal to 0, so we have the convolution product here, and it is 1/3, sum from minus infinity to plus infinity of the absolute value of sinc of k over 3, which, because of the non-absolute summability of the sinc, diverges to infinity. The divergence, however, is very, very slow. You can see here a plot that shows that for 10,000 samples, we're still below 4 in terms of the value of the sum. Now that we have the ideal low pass in place, we can obtain a series of derived filters, such as the ideal high pass filter. You can see here from the plot that we are now preserving the frequencies from omega c to pi, and of course symmetrically those from minus omega c to minus pi, and we are killing everything in between. Now, formally, we can write the frequency response of the high pass as 1 for omega between pi and omega c, and symmetrically from minus pi to minus omega c, and 0 otherwise. The 2 pi periodicity is always implicit. We can also write that as 1 minus the complementary low pass. So if we have a low pass with cutoff frequency omega c, and we take 1 minus that low pass, we obtain the high pass. So that the impulse response in time domain is actually a very simple modification of the impulse response of the complementary low pass. It's just the delta function minus the sinc function scaled by omega c over pi. Another variation is the bandpass filter. The bandpass filter preserves the frequencies in a band centered around omega 0 and 2 omega c wide, and the response is of course symmetric in the negative part of the spectrum. And we can obtain the bandpass filter starting from a prototype low-pass filter with bandwidth again 2 omega c, and by modulating this low-pass filter using a cosine modulation. So if we take a cosine at frequency omega 0 and we multiply that by the impulse response of the prototype low pass, we get one copy centered in omega 0 to omega c wide, and we get another copy in minus omega 0. We sum the two, we scale them back to unit amplitude, and we have our ideal bandpass filter. Formally, we can write the frequency response as 1 for omega plus or minus omega 0 less than omega c in magnitude, and 0 otherwise. Again, the whole thing is 2 pi periodic. And if we look at the time domain, we see that we have the standard impulse response of the prototype low-pass filter with cutoff frequency omega c modulated by the cosine of omega 0 n, and the factor 2 here scales the filter back to unit amplitude in the frequency domain. So now that we have the ideal filters in place, why don't we revisit the demodulation problem that you remember we left somewhat open in module 4.8. You remember the story. We applied sinusoidal modulation to an input signal x of n to obtain y of n, which is equal to x of n times the cosine of omega 0 n. And we tried to demodulate the modulated signal by multiplying the modulated signal again by the carrier cosine omega 0 n. And we found out that the demodulated signal contained unwanted high-frequency components that at the time we did not know how to remove. Well, now we do, so let's look again what happens. So we have the spectrum of the signal, we modulate it, and we obtain two copies, half the amplitude, at omega 0 and minus omega 0. When we multiply this signal by cosine of omega 0 again, and we can see this more in detail if we explicitly show the periodicity of the spectrum. So here you have the main minus pi to pi interval, and here you have the repetitions. So we multiply that by cosine of omega 0, and we get one copy of the repeated spectrum. Move to the right by omega 0, so you see it here in green, whereas with the dashed line you see the original modulated spectrum. And the second component would be another copy of the modulated spectrum, this time shifted to the left by omega 0. And so you have the two copies that now you have to sum together, and what you get is, of course, the reconstruction of the original signal centered around 0 and these spurious components at high frequency. So if we go back to the standard visualization of the spectrum over a single period from minus pi to pi, this is the situation we have to deal with. Well, now we know what we need to do at this point is to eliminate the spurious components, and we can do that easily by using a low-pass filter. So we put a low-pass filter here, choosing a cutoff frequency omega c that is large enough to include the main signal, the baseband signal, how it's called, and small enough in order to kill the high-frequency components. And when we do that, we obtain the original signal back without any extraneous material.